welcome back to lectures on advanced calculus for engineers, and this is lecture number 14, and in this lecture we will be again discussing differentiability, and in particular we will consider several different types of problems to investigate the differentiability of functions of two variables. So, just to recall from the previous lecture, we have defined differentiability for a function of two variables, that if we can write down this increment delta z in the form of this linear part where we have a delta x, b delta y, and these a and b are free from delta x delta y, and there is a nonlinear term here epsilon 1 delta x, epsilon 2 delta y, where epsilon 1 and epsilon 2 they both go to 0 as delta x and delta y go to 0. So, this was the definition of the differentiability, which was related to the existence of the tangent plane at a point. And for testing the differentiability, we have seen that this limit definition. So, if we compute this limit delta rho to 0, delta z minus dz over delta rho, if this limit is 0, that is equivalent to this definition, and this is easy for testing the differentiability because computing limit is relatively easier than expressing this delta z in this particular form. So, here delta rho is square root x square minus y square, and the necessary condition for differentiability which we have seen was the continuity of f and the existence of partial derivatives of f x and f y. So, both the partial derivatives should exist and the function must be continuous. These two are the necessary conditions for differentiability, and the sufficient conditions we have seen that existence of one partial derivative and the continuity of other. So, in other words, that of course, both the partial derivatives must exist as per the condition, the necessary conditions, and one of them is continuous, then we can claim that the function is differentiable. Well, so coming to this problem where we will discuss the differentiability at origin of this function f x is equal to x y cube over x square plus y square when x y is not equal to 0, and this is 0 when x y is equal to 0. So, the necessary conditions we will check first, that means whether the function is continuous and the derivatives, the first order partial derivatives exist. So, regarding the continuity, we can easily observe here that when x y goes to 0, by substituting x is equal to r cos theta, y is equal to r sin theta, that means changing to polar coordinate, we can easily realize, because here we will have r square and there we will have r 4, and then we have cos theta and then sin cube theta, and as r goes to 0, because this term is bounded, so this will go to 0. So, that means the function is continuous. We have this limit of the function as x y goes to 0, we have this limit 0, which is the function value at the origin. So, the function is continuous at the origin, and we have this partial derivative at 0, which can easily be evaluated. So, we have the definition of the partial derivative at 0 0. So, delta x goes to 0 and we have f delta x comma 0 minus this f 0 comma 0 over this delta x, and here this limit delta x goes to 0. So, delta x comma 0, because of this product, this is 0 and the second one is also 0 over delta x. So, the limit is 0. So, this f x at 0 0 is 0, and similarly f y also at 0 0 is 0. Now, coming to the sufficient conditions, because the necessary conditions are fulfilled, that means now we can, the function may be differentiable, may not be differentiable. So, let us there could be at least two ways to prove this differentiability. So, one would be taking that limit or expressing the delta z in terms of that linear and that nonlinear part. The other could be through sufficient conditions. So, we test the sufficient conditions. If they are satisfied, then we can say that the function is differentiable. So, let us check in this case. So, we need to compute this f x at all the points. So, at 0 0 we have just seen that the value is 0, and when x y is not equal to 0 0 we can directly differentiate this function with respect to x, keeping y as constant, and as a result we will get this expression here for f x at x comma y. Now, here we need to test whether this function is continuous or not. So, for the continuity again we have to see whether this limit when x comma y this goes to 0 comma 0 of x square y square plus y is y 5 and divided by x square plus y square whole square. So, we need to test whether this limit here of the partial derivative when x y is not equal to 0 comma 0, if it goes to 0, which is the function value. So, the value of f x at 0 0, then this function we will say it is continuous. So, here again as we see that x square y square terms are coming. So, it will be easier to again go for the polar coordinates. That means, by substituting again x is equal to r cos theta and y is equal to r sin theta. So, if we do that, what we will get in the denominator, that will be r power 4, but in the numerator we will get. So, this is y 3 here. So, in the numerator we will get r 5 common, and then there will be cos and sin terms. So, this r 4 will cancel with this r 5. So, we will still have one r in the numerator and together with some cos and sin. So, when the limit r goes to 0, this will go to 0. So, what we observe that this function f x x y is basically continuous, because this limit here of this f x x comma y is 0, and with this continuity, this is the sufficient condition we have on the function for the differentiability. So, f x is continuous, and therefore, the function is differentiable, because we need the continuity of one. So, we need not to check the continuity of the other one f y, because our result says that if one of them is continuous, then that is sufficient for proving the differentiability. Indeed, we have also gone through the proof of this differentiability, assuming one was continuous and both of them, the f x and f y, exist. So, here we have proved through this sufficient condition that the function is differentiable, but in case this we fail here, that f x is not continuous and f y is also not continuous. In that case, again we need to go for that limit definition, or that most fundamental definition, to prove whether the function is differentiable or not, because these are sufficient conditions. So, if they are not satisfied, still the function may be differentiable. Well, so now we discuss the differentiability at origin of this function, which is y cube and sine 1 over x square, and we have this 0, x is not equal to 0, and this is 0 when x is equal to 0. So, this is a special function somehow, because we will observe that in this case a sufficient condition does not work for one derivative. So, let us just go through and then we will discuss. So, here the continuity of f and the existence of partial derivatives we can easily see here, because when we consider this for continuity. So, if we take the limit x y goes to this 0 comma 0. So, since we have here y cube and then some sign is sitting here which is finite. So, when y goes to 0, basically this will go to 0. So, this is 0, which is the function value. So, this is equal to f 0 comma 0. So, at 0 0 this function is continuous. Similarly, the partial derivatives we can easily evaluate. So, at 0 0, for instance, if we want to compute 0 comma 0, then we need to go for this limit delta x to 0 and then f delta x into 0 minus this f 0 0 and we have delta x. So, when this y is 0, again this function will become 0. So, we have 0 minus 0 over delta x, and the limit here delta x go to 0. So, this is 0. So, the partial derivative with respect to x and also partial derivative with respect to y. So, both will be 0. Now, we compute the partial derivative x with respect to partial derivative of f with respect to x at point here x y, which could be a non-zero point where x is not equal to 0. So, basically in the whole domain we are computing this for checking the the continuity of this f x as a sufficient condition. So, here when x is not equal to 0, one can easily get by differentiating this one, because once we differentiate this with respect to x, keeping y as constant, we will get here cos 1 over x square, and the derivative of 1 over x square will be minus 1 over x 3. So, here we have this minus, so here minus 2 over x 3. So, we will get minus 2 y 3 over x 3 cos 1 over x square, that will be the derivative, partial derivative of this function with respect to x when x is not equal to 0. And when 0 0, we have just seen that the value is 0, and there is another case which need to be considered separately, that this derivative at 0 and y. So, y is not equal to 0. So, at this point we need to check. So, here as per the definition, we have the delta x to 0, and f we have delta x comma y minus this f 0 y over this delta x. So, here we have the limit delta x to 0, and this f delta x comma y will be y cube, and then sine here 1 over delta x square minus this 0 divided by delta x. So, what do we see here, that we have this y cube and then this sine 1 over x square divided by delta x, and delta x goes to 0. So, what will happen to this limit? So, sine we do not know anyway what will be the value of sine 1 over delta x square. So, this does not exist, and on the top here we have 1 over delta x. So, again here delta x goes to 0 from the right side or from the left side, again it will go to 1 over delta x will go to plus infinity or minus infinity. So, basically we cannot evaluate this limit, it does not exist because of again for the sine which is not known what is the value of this, and secondly we have 1 over delta x, and delta x 1 over delta x goes to either plus infinity or minus infinity. So, this does not exist. This is what written here, that when x is 0 and y is not equal to 0, this limit does not exist. Now, regarding the continuity of this function, so since this f x does not exist in the neighborhood of this 0 0 point. So, we are at here the 0 0 where we are testing the continuity, and what we have observed, when x is 0 and y is not equal to 0. So, here on this basically the y axis except this origin, the function is not defined in the both the sides. So, except this origin on this y axis, the function is this f x is not defined. So, we cannot take the limit as x y goes to 0. So, how to take that limit, because along this line the function itself, the f x is not defined. So, this function cannot be continuous. So, this f x is not continuous, but here we cannot conclude anything about the differentiability. First of all, this is what we are testing the sufficient conditions. So, one of them, so f x we have seen here that this is not continuous, but the sufficient condition says that one of them should be continuous, not necessarily both. So, now we test the differential for this differentiability, we test the continuity of the other one, that means we test continuity for f y. So, here we have already seen that when x is 0, this value of the derivative will be 0, because this f y at when x 0 and y can be anything basically. So, this is as per the definition, delta y goes to 0, and we have here the f and 0 y plus delta y and minus this f 0 y and divided by this delta y. So, since this first argument here is 0, so both will be 0 and then minus 0. So, this value will be 0. So, therefore, we have written here that x is equal to 0, the derivative is basically 0, and when x is not equal to 0, we can easily compute this first order derivative with respect to y from here, because x will be treated as constant. So, we have 3 y square and then we have sine 1 over x square. So, that is the derivative. Now, to test the continuity of this f y, we need to see that how this f y x y behaving as x y go to the origin. So, here when x is not equal to 0, the function has this value 3 y square cos over x square, but when x and y go to 0 comma 0, what will happen to this function? Since y is sitting here, so y goes to 0, this will become 0, and cos is anyway bounded function. So, we will not worry about that whether x goes to 0, whatever value it is, but y goes to 0, then this value will go to 0. So, here f y x y is actually continuous because this limit here is 0 and which is the function value at this 0 comma 0 point. So, f y at 0 comma 0 is 0. So, hence this f y is continuous, and now we can apply again those sufficient conditions that if one of them is continuous, then the function will be differentiable. So, this function, since f x exists and f y is continuous at 0 0, so we now claim that the f is basically differentiable at 0 0 due to that sufficient condition of differentiability. Well, we can also use limit test. So, but just in this case, just to verify that what is coming due to this limit test. So, to check the differentiability of this function, we have that limit test where we need a dz, which is the partial derivative with respect to x delta x and partial derivative z with respect to y and delta y. So, since these two partial derivatives were 0, so this dz, the total differential will be 0. And this increment delta z will be f delta x comma delta y minus f 0 comma 0. And in this case, because this f 0 comma 0 is 0, so from delta x delta y we will get delta y cube and sine 1 over delta x square. So, we have this limit delta z minus dz over delta rho. So, to compute this limit, so delta z we will put it here delta y cube and sine this 1 over delta x square and the square root of delta x square plus delta y square. Now, to see that what is happening here when delta rho goes to 0, we can just observe that if we change this delta x and delta y into polar coordinate, then it will be easier to see that this limit is indeed 0. So, changing to polar coordinate, so this is delta y r sin theta, and then we will see r square and sine of this expression here 1 over r square cos square theta, and r goes to 0, then we have this limit is actually 0. So, this f is differentiable at this 0 comma 0 point. We have already seen due to the sufficient conditions this function is differentiable. We have also tested this using the limit test, and this function is differentiable basically. Okay. So, this is another problem where f x y is defined as square root x y wherever x y is greater than or equal to 0, because otherwise this square root is not defined at all. So, elsewhere the value of this function is 0. So, we will determine here whether the function is differentiable at the origin or not. So, first again the continuity and the existence of partial derivatives we have to see. So, regarding the continuity, when x y go to this 0 comma 0, in that case the square root x y will be indeed 0, because whether we go from the region where x y is greater than 0. So, the square root x y, when x y both are tending to 0, it will be 0 indeed, and at all other point the function value is 0. So, this continuity is not an issue. Now, coming to the existence of the partial derivatives. So, we will test first the f x. So, f x is limit delta x to 0 f delta x comma 0 and f 0 0 divided by this delta x. So, f delta x comma 0. So, this is where the product is 0. So, again the value will be 0 and there here also minus 0 divided by delta x. So, here the function value is or this limit value is 0. So, this f x at origin is 0. Similarly, the f y also we can compute and then we will see that this is also 0. So, the partial derivatives exist, the function is continuous. Now, we can move for further consideration of differentiability. So, for the differentiability we need to test this limit delta z minus dz over delta rho, and for that we need this total differential where partial derivative with respect to x delta x, partial derivative with respect to y and then delta y. These partial derivatives are 0 we have seen at origin. So, this value will be 0 and then this delta z we have f 0 plus delta x 0 plus delta y, that is the increment in f minus this f 0 comma 0. So, assuming this delta x delta y greater than 0, we have this square root delta x delta y minus this f 0 0. Well, so with this delta z now we have the dz. Let us compute that limit delta z minus dz over delta rho. So, here we have the square root this delta x delta y, this is 0 anyway, and then square root delta x square plus delta y square. Now, looking at this limit, we can realize that if we take this path delta y is equal to delta x, for instance, we fix this path along this line delta y is equal to delta x and then we let this delta x to 0. So, what will happen to this limit now? We have here the square root delta x square and there also we have delta x square and plus delta x square. So, 2 delta x square. So, this limit will be 1 over square root 2, right. So, this for the differentiability this limit has to be 0, but we have seen at least for this case when we have assumed this delta x delta y positive that this limit is not 0. So, what we say now that this function is not differentiable. So, the function was continuous, the function those partial order derivatives first order partial derivatives exist, but this function is not differentiable. Well, coming to the next problem, here we will discuss again the differentiability at origin and the function is given as f x y is equal to x 5 by 2 with sine 1 over square root x and then this x we have just y for the symmetry. So, wherever x is not equal to 0, y not equal to 0, we have the function defined by this and otherwise this function is defined as 0. Well, so for this function we can prove this differentiability. So, continuity and the existence of partial derivatives is trivial, one can easily prove that. So, regarding the differentiability, we will see that this is one way, I mean not necessarily that we have to do in this way, we can again use that limit definition and then prove the differentiability. So, here we write delta z a delta x plus b delta y epsilon delta x and epsilon 2 delta y. In this form we will try to rewrite this function. So, what is delta z? Is f delta x delta y minus f 0 0, f 0 0 is 0. So, we have just f delta x delta y, that means this is delta x power 5 by 2 and the sine function here delta y 5 by 2 and then the cos function. So, what we see, we have already here this x which is not linear, here also we do not have a linear term. So, this is already 5 by 2. So, we have delta x and delta x power 3 by 2, here also the same situation. So, what we realize that this is equal to 0 into delta x, 0 into delta y, that is what we are considering for the linear term, and this will make the other terms which requires epsilon and epsilon 2. So, here delta x we take it out and then the rest we call as epsilon 1. So, delta x power 3 by 2 and then we have sin 1 over delta square root x. Delta y, we have delta y 3 by 2 and we have cos 1 over square root delta y. So, this becomes epsilon 1, this becomes epsilon 2 because both of them will go to 0 as delta x and delta y they go to 0. So, here we have expressed this delta z in this form epsilon 1 epsilon 2 form, and therefore, this function is differentiable. Well, so here we have another problem on let f x y is equal to 0 and 1. So, 0 when x y is not equal to 0 and this is 1 when x y is equal to 0, the product is equal to 0. So, we check the existence of f x and f y at the origin and then we will see whether the function is differentiable or not. So, f x we test here. So, delta x to 0 f delta x 0 minus f 0 0 over delta x, and then this f delta x comma 0. So, here the product is 0. So, the product is 0 means the value is 1, minus here also the product is 0. So, the value is also 1. So, 1 minus 1 over delta x, the partial derivative f x is 0. Now, the partial derivative y. So, we have delta y to 0, we have f 0 delta y minus f 0 0 over delta y. So, again with the same logic. So, this x y 0 means here also 1 minus 1, this is also 0. So, the partial derivatives at origin exists, this is the value 0 and here also we have the value 0. Now, the continuity check of f we will do. So, the partial derivatives exist. So, now we have to check for the differentiability, that means the other necessary conditions we need to check. So, we check the continuity of f. So, what is happening for the continuity when x y is not equal to 0. So, wherever x y is 0, whether this axis or that axis, so x axis, y axis, everything is 1, the value is 1, and wherever we have for instance this line here x is equal to y line. So, x y is not equal to 0 on this except that origin. So, the value is 0 of the function is 0 at this line. So, suppose we approach along this line to this origin, this is origin. So, if we approach along this line to this origin, what will happen, because at all points on this line the function has value 0. So, in the limiting case also, because for whatever x and y you take on this line other than that origin point, the function value is 0, hence that will be the limit, but the function is defined as 1 at the origin. So, there is a problem in the continuity part. So, suppose this limit x y goes to 0 along, if you take x is equal to y, where x y is not equal to 0 basically, and then the value of the function at any point on this line other than that origin is basically 0. So, this limit is also going to be 0 and the function value at that point is 0 because of this definition here. So, this is not equal to f 0 0, hence the function is not continuous. So, though the partial derivatives exist, but the function is not continuous, then what we can say about the differentiability? Naturally, these necessary conditions are not satisfied, hence the function is not differentiable. Function is not continuous and hence the function is not differentiable at 0, 0 point. Well, so this is the last example we will be discussing for differentiability. Here the f x y is defined as x square plus y square over absolute value of x plus absolute value of y, where this x y is not equal to 0, 0 and x y is 0, 0, then this is defined as 0. So, to check this differentiability, we will go through the continuity check first. So, to check the continuity, since this mod x mod y is coming there, and it will be easier to test this continuity using the epsilon delta approach. That means, we check this difference f x y minus this 0, 0 is the function value here. So, this is f 0, 0 and see whether this difference we can make as small as we like. That means, for any given epsilon, can we make this less than epsilon, and for that epsilon can we find out the delta. So, delta neighborhood of that origin. Well, so let us proceed with this. So, we have here x square plus y square over mod x plus mod y. This x square plus y square will be smaller than the mod x plus mod y whole square, because here there will be an extra term to mod x mod y. Therefore, this is bigger quantity than x square plus y square, and this is as it is mod x plus mod y. So, that means we have mod x plus mod y in the numerator itself. Now, we need to relate this, or we need to have an inequality where we can relate this mod x plus mod y to x square plus y square or square root of x square plus y square. So, this was already discussed in one of the previous lecture, that this is less than square root 2 and square root x square plus y square. And now we have this square root x square plus y square, that is the delta neighborhood of 0 comma 0. That means, this is less than square root 2 delta, the delta neighborhood, and at this point we can relate the delta and epsilon, because this everything we want to set to less than epsilon for any given epsilon. And then if we choose our delta from this relation, that delta is less than equal to epsilon by square root 2, then this difference f x y minus this 0 can be made arbitrarily small. So, if we choose this delta less than or less than equal to epsilon by square root 2, in that case this difference is less than epsilon, and hence the limit of this function is exactly this 0, and basically this function is continuous. So, the continuity is tested here, function is continuous. Now, for the existence of partial derivatives, which is also not difficult. So, f delta x 0 f 0 0 over delta x. So, f delta x y 0. So, that means you have here delta x square over this delta x is there, and then we have delta x absolute value. So, this turns out to be delta x over absolute value of delta x. And now, when delta x goes to 0, because this absolute value of delta x, so this is anyway will go to 0, but here it will go to when we approach delta x from the positive side. So, if delta x goes to 0 from the positive side, it will be like delta x over delta x, and the value will be 1. But when we approach delta x to 0 from the negative side, then this delta x and divided by this is minus delta x, and this value will be minus 1. So, this limit does not exist, and hence this both the partial derivatives must exist for the differentiability, but we have seen that one of these partial derivatives does not exist. So, hence this function cannot be differentiable, f x at 0 0 does not exist. And similarly, we can also show for f y 0 0, because this function is just a symmetric function. So, the function is not differentiable, though just showing one is enough. So, if one derivative does not exist, we can just without checking the other one, we can immediately say that the function is not differentiable at the origin. Well, so just to conclude, we have gone through various examples in this lecture on differentiability, where sometimes we have used the necessary conditions to prove that this is not differentiable. Sometimes we have used the sufficient conditions to prove differentiability. Sometimes we have used limit definitions to prove differentiability. Sometimes we have used that most fundamental definition, where we express delta z into this epsilon 1 epsilon 2 form. So, we have considered various ways where the differentiability can be discussed of a function of two variables. So, the continuity and the existence of partial derivatives are necessary conditions for differentiability, where as we have seen that continuity of one of the partial derivatives, and in fact, there was one example where only one partial derivative was continuous and the other one was not continuous, and therefore, because of this result the function became differentiable. Also, this limit test which we have seen, it is very useful to test differentiability, or sometimes we have this most fundamental definition of the differentiability to test for a particular problem. Well, so with this, so these are the references we have used for preparing this lecture, and I thank you for your attention.